In this lecture video, we're going to start looking at inferences about a population variance. In particular, we're going to be looking at how to construct a hypothesis test for a population variance, and we'll also look at point and interval estimation of a population variance. So the sampling framework is as follows. Let x1, x2, and so forth up to x sub n be a random sample of size n from a normal distribution with mean mu and variance sigma squared. Let x bar be the sample mean, and let sigma hat squared be equal to s squared, the unbiased version of the sample variance. In addition, let's let sigma hat, which is the square root of sigma hat squared, be the sample standard deviation. Now, since we're sampling from a normal distribution, the random variable, which we will denote by chi squared, equal to n minus 1 times sigma hat squared over the population variance, that random variable has a chi-squared distribution with n minus 1 degrees of freedom. Now this result about the sampling distribution of this version, or this transform version of sigma hat squared, will be the basis for hypothesis test and confidence interval procedures that we're going to be looking at. So let's first consider testing the hypothesis that sigma squared, the population variance, is equal to a hypothesized value, sigma 0 squared, against the alternative that the population variance is not equal to that hypothesized value. And let's perform this test at a significance level of alpha. And so the questions we need to consider in order to come up with a test is first, how does sigma hat squared, the estimator of sigma squared, behave under the conditions of the null hypothesis? Second, how does sigma hat squared behave under the alternative hypothesis? And can the differences in the behavior of sigma hat squared under the null hypothesis and under the alternative hypothesis be used to come up with a way of distinguishing between when the null hypothesis and alternative hypotheses are true? So if the alternative is true, in other words, if the population variance is not equal to sigma naught squared, then sigma hat squared will tend to be different, farther away from the hypothesized value than it would if the null hypothesis were true. So for example, if the population variance is less than sigma naught squared, then sigma hat squared would tend to be smaller than the hypothesized value sigma naught squared. And if if sigma squared is greater than sigma naught squared, then sigma hat squared would tend to be larger than sigma naught squared. So those are what we're looking for: small values of sigma hat squared or large values of sigma hat squared. Values of sigma hat squared that are much different than the hypothesized value sigma naught squared. Those are the kinds of situations that we're going to be looking for to lead us to reject the null hypothesis. Now we need to quantify this probabilistically in order to come up with the appropriate critical points. And so we know, based on what we've said about the sampling distribution of n minus 1 times sigma hat squared over the actual variance, we know that if the null hypothesis is true, in other words, if sigma squared is equal to sigma naught squared, then the probability that sigma hat squared is between these two values, this lower and upper value, that probability is 1 minus alpha. So what you need to do is make sure that you understand why this is true. And it's going to be based on what we've said about the sampling distribution of n minus 1 times sigma hat squared over the population variance of sigma squared. So the probability of observing a value of sigma hat squared between these two endpoints, if the null hypothesis is true, is 1 minus alpha. And so by the complement rule, the probability of getting a hold of a sample for which sigma hat squared is is outside of this interval, is going to be 1 minus alpha. So that's what this probability statement is saying. the probability of getting a hold of a sample for which sigma hat squared is either less than the lower endpoint of that interval or greater than the upper endpoint is alpha. And so these are the values that we'll be using for the critical point, or critical points, I should say, since we have more than one. Okay, and so this leads us to the acceptance region, which are the two endpoints, or the interval defined by the two endpoints that we've just identified. This is the set of values of sigma hat squared that are consistent with the null hypothesis, and therefore would not lead to its rejection. It would lead to the acceptance, so to speak, of that null hypothesis. On the other hand, we can, if we look at the complement of that interval, then we get the rejection region. So then translating this into decision rules, we would accept the null hypothesis if sigma hat squared is between these two endpoints, and we would reject the null hypothesis if sigma hat squared is either less than the lower endpoint or greater than the upper endpoint. Now we can translate these decision rules from rules involving sigma hat squared into rules involving sigma zero squared, the hypothesized value of the population variance, as you can see here. And so with that in mind, then we can think of plausible regions and implausible regions for the population variance. And so the plausible region, for a fixed value of sigma hat squared, computed from the data, obviously, then for a fixed value, then the plausible region would be given by this interval. This is a set of plausible values for the population variance in the sense that the null hypothesis, sigma squared equal to sigma naught squared, would not be rejected in favor of the alternative for any value of the hypothesized value, sigma hat squared, in that interval. And this, again, this interval is based on the observed value of sigma hat squared. The implausible region would be the complement of that interval, so the union of these two intervals. And so based on the observed value of sigma hat squared, the null hypothesis, sigma squared equal to sigma naught squared, will be rejected in favor of the alternative for any value of sigma naught squared in that union of intervals. Next, let's consider what we might call a left-tailed test, because if we look at the alternative, it's stating that sigma squared is less than a particular value. So the null hypothesis in this case is that the population variance is at least, it's greater than or equal to this hypothesized value, sigma naught squared, against the alternative that the population variance is less than that hypothesized value. And as usual, we're going to denote the significance level of the test by alpha. And so, again, what we need to do is, in order to come up with, to motivate a test, we need to think about how this sigma hat squared behaves under the conditions of both the null and alternative hypotheses. And if that behavior is different, then can we use that differential behavior as a way of discriminating or differentiating between the null and alternative hypotheses? We need to be able to identify or come up with a way of trying to identify which of those two hypotheses is the true state of nature. And so if the if the alternative is true, in other words, if the true population variance is less than this hypothesized value, then sigma hat squared would tend to be smaller than it would be if, in fact, the null hypothesis were true. And so intuitively then, small values of sigma hat squared will be evidence against the null hypothesis. And so as usual, we need to quantify this probabilistically so that we can determine the appropriate critical point to use for the test, a critical point that gives us a significance level of alpha. And so we use what we know about the sampling distribution of n-1 times sigma hat squared over sigma zero squared. And we're going to be considering what happens on the boundary of the null hypothesis space when sigma squared is equal to sigma hat squared, or sigma naught squared. And so anyway, with that in mind, the probability that sigma hat squared is greater than or equal to this quantity would be equal to 1 minus alpha. And so again, I'm thinking specifically about what happens at the boundary condition. And therefore, by the alternative hypothesis, by the complement rule, then the probability that sigma hat squared is less than this value is alpha. And so that leads us to an acceptance region and a rejection region. Values of, for a fixed value of the hypothesized value, sigma naught squared, for values of sigma hat squared in this interval, we would not reject the null hypothesis. These values are consistent with the null hypothesis. Remember, the null hypothesis says that sigma squared is greater than or equal to sigma naught squared. And so this set of values for sigma hat squared would be consistent with the null hypothesis. On the other hand, values of sigma hat squared in this interval would be considered inconsistent with the null hypothesis, and at a significance level of alpha, we would reject the null hypothesis for any value of sigma hat squared in this interval. All right, and so we can again restate this in terms of decision rules. And so we would, based on the acceptance region and the rejection region, we would accept the null hypothesis if sigma hat squared is greater than or equal to this quantity, and we would reject the null hypothesis for small values of sigma hat squared, in particular values of sigma hat squared less than this quantity. All right, and we could restate each of these into statements involving the hypothesized value, sigma naught squared, as you see here, and doing so would lead us to specify plausible regions and implausible regions for sigma squared. And so we've seen this before, we've talked about it before, so I'll let you read through that to make sure that you understand that. And then finally, let's consider what we would call a right tail test. So the null hypothesis is that the population variance is less than or equal to some specified value, sigma naught squared. And the alternative would be that the population variance is greater than that value. And so again, we're going to denote the significance level by alpha. And so again, in order to motivate a test, we need to think about how sigma hat squared behaves under the conditions of the null hypothesis, how it behaves under the conditions of the alternative hypothesis, and then use that difference in behavior to come up with a way of distinguishing between the two possibilities, null and alternative hypotheses. And so it should be fairly clear that if sigma hat squared, if the population variance is less than this hypothesized value, then sigma hat squared will tend to be small as well. Remember that sigma hat squared is the unbiased estimator of sigma squared. And so the mean of its sampling distribution is equal to sigma squared. And so if sigma squared is smaller than sigma naught squared, then the probability distribution or the sampling distribution of sigma hat squared is going to be centered at a point that is less than or equal to sigma naught squared. And so then the probability of observing a value of sigma hat squared that's fairly small will be larger than it would be if in fact the alternative were true. If the alternative is true, then the sampling distribution of sigma hat squared will be centered or have a mean, let's put it that way, right? At some point that is to the right of sigma squared. And so that's basically what we're saying here on this next slide. If the alternative is true, then sigma hat squared will tend to be larger than it would be if the null hypothesis were true. And so therefore, larger values of sigma hat squared are going to be what we're going to be looking for and provide evidence against the null hypothesis. So again, quantifying these intuitive notions probabilistically, the probability, if the null hypothesis is true, right? If the null hypothesis is true, then the probability that sigma hat squared is less than or equal to this quantity, this value, is going to be 1 minus alpha. And by the complement rule, the probability that sigma hat squared is greater than that value would be alpha. And again, both of these probabilities are conditional on or based on the assumption that the null hypothesis is true. All right, and so then we get the acceptance region for a particular value, or based on a particular value of sigma naught squared. And again, this is the set of values for sigma hat squared that are consistent with the null hypothesis and would lead to its acceptance. The complement of that set is this interval, okay, from this lower endpoint up to positive infinity. It's an open interval on both sides. And so these are the set of values of sigma hat squared that are inconsistent with the null hypothesis, and therefore which would lead to its rejection at a significance level of alpha. And we can translate each of these into decision rules. So we would accept the null hypothesis if sigma hat squared is less than or equal to this threshold, this quantity, this critical point. And we would reject the null hypothesis if sigma hat squared is greater than that point. And so then, again, we can also think in terms of plausible and implausible regions. Okay, and so then, those are the 3 kinds of tests that we can consider. And so let's now put these all together and come up with the procedure for testing hypotheses about a population variance. And so we have our two-tailed test, we have our left-tailed test, and we have our right-tailed test. The same kind of tests that we have when we're testing hypotheses about a population mean. All right. So the null hypothesis for the two-tailed test, the null hypothesis is that the population variance is equal to a particular value, sigma naught squared. The alternative is the opposite of that sigma squared is not equal to that value. And so if the goal of a research project or a research question is to show that the variance of a population is different than a particular value, then we would use this two-tailed test. If the purpose of a project or experiment, or perhaps we have a decision-making situation in the context of manufacturing or business or whatever, if the purpose is to show that the population variance is less than a particular value, then we would use a left-tailed test. So the alternative would be that the population variance is greater than or equal to a particular value. The alternative would be that the population variance is less than that value. And then finally, we have the right-tailed test. So the null hypothesis would be that the population variance is less than or equal to some specified value against the alternative that the population variance is greater than that value. And so these are the 3 kinds of tests that we can perform about a population variance. And we've gone through the process of thinking about starting off with a point estimator for the population variance and thinking about how that point estimator behaves under the condition of the null and alternative hypothesis for each of these 3 kinds of tests. And we've used that behavior, our understanding of the sampling distribution of that estimator to motivate and come up with testing procedures that we're now summarizing. And so the formula for the test statistic that we will use will be, we're going to call it chi-squared calc. And here I'm denoting, I'm using s squared instead of sigma hat squared. All right, we just need to be familiar with both of those pieces of notation and comfortable using either one of those in a given situation. All right, so this is the formula for the test statistic, And notice that in the denominator, we have the hypothesized value of sigma squared, all right? And then we know that under the conditions of the null hypothesis, the sampling distribution for this test statistic is the chi-squared distribution with n minus 1 degrees of freedom. And then if we are, then we have the rejection criteria. And so if we are performing a two-tailed test at a significance level of alpha, then we are going to reject the null hypothesis if our test statistic is strictly less than the upper 1 minus alpha over 2 percentage point of the chi-square distribution with n minus 1 degrees of freedom. And we're going to reject the null hypothesis if that condition is true, or if the test statistic is greater than the upper alpha over 2 percentage point of the chi-square distribution with n minus 1 degrees of freedom. If we are performing the left-tailed test, then we will reject the null hypothesis for small values of the test statistic. In particular, values of the test statistic that are less than the upper 1 minus alpha times 100% confidence, the 1 minus alpha percentage point of the chi-square distribution with n minus 1 degrees of freedom. And then finally, if we're performing a right-tailed test, then we would reject the null hypothesis for values of the test statistic that are greater than the upper alpha percentage point of the chi-square distribution with n minus 1 degrees of freedom. Now, one thing I want to point out is that when we performed hypothesis tests about a population mean, the lower critical points for the two-tailed test and for the left-tailed test, we stuck a minus sign in front of those. Those are the critical points. But we don't do that here for the tests involving a population variance because the variance has always got to be positive, all right? And the estimator of the population variance will always be positive as well. And so when we state the critical points, the lower critical point for the two-tailed test and the sole critical point for this left-tailed test, then notice that there's no minus sign there, but we're specifying the upper probability area here in the subscript. And so, for example, if alpha were equal to 0.05, if the significance level of the test was 0.05, then this would correspond to the upper 0.975 percentage point of the chi-square distribution. And this point would correspond to the upper 0.95 percentage point. So I think let me bring up the chi-square table just so that we can look at this and we can make sure that we understand what we're talking about when it comes to obtaining this lower critical point for the two-tailed test and this particular critical point for the left-tailed test. And so here is the chi-square table that is available to you on Moodle. And these, on the top row, these are the right-tailed areas under the corresponding chi-square distribution with a given number of degrees of freedom. Right tail areas to the right of the critical points, or the points here that are listed in the body of the table. And so, for example, if we were to look at the chi-square table with, or the chi-square distribution with 15 degrees of freedom, we would see that the probability that a chi-square random variable with 15 degrees of freedom being greater than or equal to 6.262 is 0.975. All right, and the probability that a chi-square random variable with 15 degrees of freedom is greater than 27.488 is 0.025. So you see how here that we have to have the columns for upper tail probabilities that are fairly large because we don't get the lower critical points of these kind of tests just by looking up values like we did in the t-table and then putting a minus sign in front. So anyway, that's how this table works. That's the structure of this table. Hopefully that makes sense. We're going to get practice with that. Okay, so these are the rejection criteria for the three types of hypothesis tests: the two-tailed test, the left-tailed test, and the right-tailed test. And so what we'll do next is look at an example. And so we're going to go back and revisit this example where we are filling jars of peanuts, 8-ounce jars of peanuts, with a machine. So in filling the jars with peanuts, we not only want the average weight of contents to be 8 ounces, but we also want to maintain a degree of consistency in the amount of peanuts being dispensed into jars. If one jar receives too many peanuts, it will overflow and waste peanuts. If another jar gets too few peanuts, it will not be full and the customer of that jar will feel cheated, even though on average, the jars have the specified amount of peanuts. Therefore, a test of the variance of weights of peanuts should also be part of the quality control of the process. So in previous examples, we have talked about the process being in control if the average weight of peanuts being dispensed is 8 ounces. But what we realize is that that's only one aspect of the process being in control. If there's wide variation in the weights of peanuts being dispensed, then that is bad as well. So there are two aspects, really, two considerations when it comes to thinking or determining whether or not, or defining what it means for the process to be in control. Number one, the average weight of peanuts has to be 8 ounces, but also we want the variability associated with the fill weights to be less than a particular value. And so how are they going to quantify that? And so the author of the textbook likes to express these criteria involving variability in this way. And so what he says is that suppose the weight of peanuts in at least 95% of the jars is required to be within 0.2 ounces of the mean. So that is one way of, and it's an indirect way, but it's one way that makes sense for stating something about the variability associated with the process. And it's doing it in terms of, it's stating it in terms of the percentage of the jars that have fill weights within a certain distance of the mean. So formulate and perform the test to check this. And in this example, we're going to use a significance level, in this case, of 5%. All right, so we're just picking, I'm sorry, 1%. 1%, I said 5%, 1%. And we're just picking that so we're going to make it, if we'd picked 5%, we could do that. By choosing 1%, it's going to be harder than it would be at using a 5% level to reject the null hypothesis. So in order to set up the null and alternative hypotheses, we have to translate this statement, okay, this criterion that needs to be satisfied, we need to translate this into a statement about the population standard deviation or the population variance. And so again, the statement is, and this is the criterion that must be satisfied in order for the machine to be in control with respect to variation, is that the weight of peanuts in at least 95% of the jars must be within 0.2 ounces of the mean, whatever the mean is. And so here is a picture of what this means, what this represents. So we're going to denote the mean of the population. I've got here listed 8, but in general, we can just use mu, because regardless of what the mean actually is, for this aspect of control, we need the variation to be within certain limits. And so what this statement is saying is that at least 95% of the fill weights, and so this, the horizontal line correspond, or this is where the fill weights live. And so what this statement is saying is that the proportion of the fill weights must within 0.2 ounces of the mean, whatever the mean is. So from mu minus 0.2 up to mu plus 0.2, the proportion of fill weights must be at least 0.95. And so what that corresponds to in this case, and I'm using a normal distribution here, all right, to represent this, but that probability, the area under this normal curve between these 2 points, mu minus 0.2 and mu plus 0.2, must be at least 0.95. And so we can take that and we can translate that into a probability statement. And so the stated requirements imply that this probability, and so if X is the fill weight of the weight of peanuts, the fill weight for a randomly selected jar, then that probability that X takes on a value between mu minus 0.2 and mu plus 0.2 must be at least 0.5 or 0.95. And I'll consider that a boundary condition. So set that equality there. I can restate the probability in terms of the standard normal random variable, Z. And so then in simplifying, this implies that the probability of a standard normal random variable being between negative 0.2 over sigma and positive 0.2 over sigma, that probability must be 0.95. Now, from the standard normal table, we know that the probability that a standard normal random variable is between, and I've got 0 here, let me fix that real quick, that should be a negative 1.96. Okay, so again, we know from the standard normal table, we know that the probability that the standard normal random variable is between negative 1.96 and positive 1.96 is equal to 0.95. Now, these two results imply that 0.2 over sigma must be 1.96, which we can solve for sigma and then square it to get a statement involving the variance being equal to 0.0104. And so we're going to go ahead and round this to two decimal places. That'll be sufficient for our purposes. And so the population variance can be no more than 0.01. And so we can now set up the hypotheses. Let sigma squared denote the variance of the distribution of the weights of peanuts being dispensed into 8-ounce jars by the machine. The hypotheses to be tested for this aspect of the machine being in control are given by the following. The null hypothesis, which corresponds to the machine being in control, is that the variance of the population of fill weights can be no more than 0.01, and the units obviously would be ounces squared. The alternative, which corresponds to the machine being out of control with respect to variability, would be that the population variance of fill weights is greater than 0.01 ounces squared. Now, again, as usual, we're using a sample size of 16, and so there are 15 degrees of freedom associated with this test. And again, as stated, the significance level that we're going to use here is alpha being equal to 0.01. Now, from the chi-square table, we find that the critical point, the upper 0.01 percentage point of the chi-square distribution with 15 degrees of freedom is 30.578. So let me bring this up, and let me see here. So we're again looking at the row corresponding to 15 degrees of freedom, and what we need is the 0.01 upper percentage point, and so that value is 30.578. And so you can see that's where we get this. And so we're going to reject the null hypothesis if our test statistic, chi-squared calc, is greater than 30.578. All right, now we have set the test up, and then we collect our data, we get our sample, and we calculate the sample statistics, and in particular the sample variance. All right, and so S squared, the sample variance, well, the sample standard deviation is 0.1782, rounded to 4 decimal places for this data set. And so the variance, the sample variance, would be the square of that. And so we would plug that into this formula for chi-squared calc, our test statistic, and we end up getting a value of 47.633, rounded to 3 decimal places, which is the same number of decimal places provided by or given in the chi-square table. Okay, and again, notice that we divide in this formula. We're dividing by sigma naught squared, which is the value, the hypothesized value of that population variance. And so, since 47.633 is in fact greater than 30.578, we reject the null hypothesis and conclude that the alternative is true, which says that the variance of the population of fill weights is greater than 0.01 ounces squared. And so there is sufficient evidence at the 0.01 level of significance to conclude that the variance of the distribution of fill weights is greater than 0.01. All right, that's greater than the maximum allowable variation. And so therefore the machine, while it may be in control with respect to the population mean of fill weights being dispensed, in a given situation, it may be that may be satisfied, but here in this situation, the machine is out of control with respect to variation. And so therefore, the machine should be shut down and adjusted, recalibrated, tuned up, whatever they're going to do to it.